So, well, so these are the only two variables you have here, the cutter diameter and the surface feet per minute. So basically the surface feet per minute only changes the RPM. That's all it deals with. So you cut something at a higher surface feet per minute, you got a higher RPM, we're talking about more heat, right? This is how we control our heat basically in our cut. That's what it's all about. And where do we want that heat to go? In the chip, right? You don't want that heat to go in the tool, you don't want that heat to go in the part, you want it to be ejected into the chip. And if you're going too fast, that heat won't eject in that chip. The heat will be stuck in the material, it will be stuck in the tool, something will break, right? If you're going too slow, usually the problem is the heat is ejected quickly enough that the tool will start rubbing. And it's bad for tool life, really, if you're cutting way too slow. But that depends on your feed rate as well. So you can usually get away with cutting too slow, but it's not recommended. Like a lot of guys who are very new to machining, they're like, oh, I'll run really slow, and that should be fine, but then they break their tools. So feed rate, we're talking about inches per minute here usually. In the metric system, if you're cutting something, it's usually millimeters. Sometimes you'll see it in centimeters. It depends on the machine. And what this is the feed per tooth times the number of teeth times the RPM. So you can see right away that the RPM has a huge effect on your feed rate. They're linked very closely. And the ratio between them is very important. So like if I bump up my feed rate, or if I bump up my speed for some reason, I slow down my speed on my mill for some reason, I also got to change my feed rate.
I'm confused again. I thought IPM was
Feed rate, inches per minute.
that's your down. And what was LL?
LL. Oh, CL, cutting chip load. Sorry.
So that
Chip load is F. F is chip load. Feed per tooth, chip load, they're the same thing. You'll see it a lot both ways.
So I had the same equation right down here. That was up there.
Yeah, that's the same thing. Exact same thing.
Because there was different letters.
Yeah, it's just different variables. You guys gotta get used to that because there's a lot of discrepancies in the machining world. Some people tell you different things and you gotta know what they're talking about. But it's all the same formulas. So let's do one of these. So what are we talking about here? We're talking about how fast my tool is being fed into the part, right? Or if you actually want to think about it as the tool being stationary and the part being fed, whichever way, whatever works for you. How fast this tool is moving in relation to this part, right? So we're talking about the speed of the actual tool moving.
What would be the word for going into a part?
That's also the feed rate.
Alright.
It doesn't matter if I'm cutting this way or this way.
Okay.
It's still feed rate. So you can have a feed rate with a drill bit.
Okay.
You usually don't use an in-middle plug straight down, but you can. So let's do one of these. So let's see, what do we have? We want to figure out the IPM, which is the feed, which, if you were CNC programming, is just the F, right? Getting ready for CNC, we're talking about the F here. So that's all the machine knows, is how fast to feed that tool. So if you tell it 100 inches per minute, and it actually needs to be at 10, you're going to break something. So, let's see here. Let's do let's say this cutter's got 4 teeth, 4-tooth cutter. We're spinning at 2,500 RPM. Alright, I don't know what the cutting speed is there. You can figure that out if you want. And the feed per tooth. What material do we want to cut here? What material do we want to cut? Just throw it out. Steel. So we're cutting steel. So let's do a feed per tooth of 2 thousandths. Alright? So 2 thousandths, right? So you just multiply them all together. So F equals times 4 times and that equals 20 inches per minute? That's totally believable. I would,
Solid numbers.
those are some
Be
solid
throwing
numbers
out
right
there.
there. Solid numbers. So,
So what happens if you get something where it's a really long decimal?
Attention all Cincinnati State faculty, staff, and students. Anybody parked on Central Parkway in front of the college is going to be towed or blocking the construction lane for Cincinnati Police Department. Attention all faculty, staff, and students. Anybody
I guess that's no good here.
I'm in the garage.
Somebody's dipping out of the classroom.
You hear all these doors swing open.
For the bridge overpass being torn down this evening.
All right, we get it.
Your vehicles immediately.
Get out there and
Disrupting.
party boots on.
Seriously. All right, so 20 inches per minute, that's a reasonable feed, I'd say.
Thought it was like on fire or something.
I know, I was hoping it wasn't a fire alarm. So,
It's not raining. We'd have been cool.
yeah. So let's bump up this feed per tooth here to 5,000. What's that going to do to our feed rate?
Increase
Yeah, it's going to increase it. By how much?
by 30. We went to 50.
50. See, that's a huge deal right there. Because we're talking about 4-tooth cutter.
So if you went to a 3-tooth cutter,
You'd have to drop the feed, right? So let's do that. Let's go to the 3-tooth cutter.
Same
but
point
wouldn't
zero
the
zero five.
3-tooth cutter be taking more because the chiplet's bigger?
37 and a half.
So that's 37 and a half with this chip load, right? With this
Yes.
chip load. So 37 and a half. So look, quick little thing here. So say I'm cutting at 20 inches per minute with a 2-tooth cutter, right? And I break my 2-tooth cutter. It just breaks out of nowhere, and I have to put it in a 4-tooth. What do I have to do to my feed rate? I got to double it. Just immediately, you know you've got to double it because this doubles. And these are all multiplied. So you can just think of these as constants, really. And then what matters right there is
That's
how many
very-
teeth. So if something like that happens, you should know immediately you got to bump up that feed. Right? So you're going to have to start cranking faster. Or what's going to happen to the chip load? Say for example, I'm cutting at 2,500 RPM, right? And I've got a 2-tooth cutter, and my chip load is, who knows, and I change to a 4-tooth cutter. What's happening to my chip load there? Does it go down or up when I change from a 2-tooth to a 4-tooth?
Doubles.
Yeah,
Went to 50. It was 25 at 2, so it went to 50.
yeah. So that's something to watch out for.
Doesn't the chiplet
If-
change when you change so many teeth?
No, I'm saying same feed, same speed. F is the same. Without changing my feed. So if I program my CNC machine here to feed it 20 inches per minute, right? I break my 2-flute tool. I don't change any of the settings in the machine. I put in a 4-tooth tool. My chip load is going to change. I didn't have to do anything to change that. It changed because I changed the number of teeth. Because that means the teeth have to work harder or less hard depending on how many teeth you change to. Making sense? It's simple. It's simple stuff, but it's not super easy to get right away. You kind of got to get used to this stuff. So,
I'm just trying to figure out why the chiplet doesn't change when you put in a different.
at the same feed, it won't change. If you change the feed rate, the chip load will stay the same. Here, look.
Because the chiplet is to
No, it has nothing to do with how fast. The chip load is how much each tooth is cutting. So,
Only for that specific material.
yeah, and that specific tool. It depends on the tool, depends on the material, depends on your depth of cut, depends on your step over. Right? There's 4 things it depends on. So you usually get that off a chart somewhere. But you gotta know, if I change these teeth and everything's the same, the feed rate's the same, the speed's the same, and all I change is the teeth, the chip load's gonna change. Right? That's important. Because I've seen a lot of guys swap out tools without even thinking about that, and then they'll really mess up. Alright, so service speed per minute, if you want to calculate this, it's very useful to calculate. I use it all the time. So you can just solve for this, or you can use this this constant right here. I prefer using the constant. So let's say, for example, our Bridgeport back there, we're cutting at 3,600 RPM, and we're cutting aluminum, right? So we want to be in the range of 500 to 1,000, somewhere in there, maybe even higher. We're cutting with a 5/8 tool. Right? So, what's our service speed? $5.85.
Yeah.
So $5.85. That's a pretty good service fee per minute for aluminum. You're gonna have an all-right surface finish. You could go better probably, but if I was doing a production job,
585 feet a minute.
585 surface feet per minute. So that tool is traveling 585 feet in a minute. 1 minute, it can travel that much. And remember, you're talking about the rotational, right? So just think about one chip moving along the surface, or the 1 tooth. So that's kind of useful to know if you're in a good range or not. Like, with your machine, you can't really choose a lot of things about it. You can calculate that and say, oh, I'm in a decent range. Like, if I wanted to bump up my service speed, if I want my cutting speed, that's what CS is, cutting speed. Service speed per minute, cutting speed. If I want my cutting speed to go way up, what do I need to do with my tool diameter?
Drop it.
Do I want to drop it or raise it?
Raise it.
So I want to go to like a 1.5 inch tool. What's that do to my speed?
144.
Huh?
So it goes up.
So it goes up. The bigger tool, right? At the same RPM, that means the outside's spinning faster versus here. Same rotation, right? It takes more time. Like if I got this circle here, and I want to pass this line, this dot, that dot's going to be going way faster. It's going to take the same amount of time to get around, so it must be going faster, right?
That's what confused me. Oh, my voice is cracked. That's what confused me about when you were doing the illustration with the car wheel smaller and you moving faster.
Yeah.
That's what confused me when you showed us that 2 weeks ago.
This same thing?
Yeah,
circles.
because it seems inversely related. I would think that it's the same thing, but it's not.
I mean, it's the same thing. You're just looking at a different facade, basically. It's pretty much the same concept, though. Just remember, like these are always going to rotate. They're always going to pass this line at the same time.
At the same time.
Right? But the outside's going to be much faster. The actual linear velocity is going to be higher.
But the inside would